So it's my pleasure to introduce Zach Norwood, who is going to speak about the triangular embedding theorem today. Go ahead.
This meeting is being recorded. Yes, thank you very much for having me. I hope you all will feel welcome to interrupt as you would at an in-person talk if you have a question or a comment. I'm also not, I was trying to see who is showing up. I'm not totally sure what the composition of the audience is. I will try to give some definitions and so on for those of you who may not be familiar with some of this work, and I will try not to bore those of you who are very familiar with it, but this is a difficult line to tread, so I will do the best that I can. Okay, and I am used to watching the chat from teaching my students who refuse to speak out loud, but I will also try to watch it here in case someone has a question. But maybe if I miss it, one of the Gunter or Vika will let me know that there's a question. Okay, so this talk is about a theorem that came up in my proof with Itai Niemann that 80 plus implies that there are no infinite mad families, among other things. The reason I titled the talk this is because I want to advertise the theorem. I think in particular there should be more applications of it than are currently known, and I think there may be some extensions and variants of it that ought to be studied in more detail. So the first thing is arrow. What am I going to talk about? So. Oh, how long is this supposed to be? Should have asked that before. An hour?
You can use up to 1.5 hours, even a little more than that. You can also just, so we are flexible. So 1 to 1.5 hours usually, yeah.
It depends on how many questions people have, I guess, but I will, I won't use more than 1.5 hours.
Sounds good.
For sure. But okay, so at the beginning, I want to give you some of the combinatorial background for this theorem. Why would you try to prove this theorem in the first place? What is it good for? And then we will wait for 2 sections until I tell you what it's actually good for. But I want to give you a sense of the combinatorial background because the problems that I cared about going into this work were are entirely combinatorial and didn't, on the face of them, have anything to do with generic absoluteness or this kind of funny variant of generic absoluteness. So that's where we'll start. And then I will tell you about the actual embedding theorems. And then what are they good for? What things can you use them to prove? And I'll talk briefly about consistency strength and some related questions. 4 and 5 are really just one big section about consistency strength, and then a bunch of questions that I have.
I have a question.
Yeah, great.
Just to get me in the start, is this like an inner model theory talk or more of a forcing in large cardinals?
No, it is more of a forcing in large cardinals talk.
Oh, okay.
Yeah, maybe I should have advertised that in the what's it called? Abstract. Okay, so yeah, what are we doing here? I have to begin with the definition of happy family, or as more sober authors call them, selective co-ideals. The definition, if you have not seen it before, this is what you should think of. Hold in your head the proof of infinite Ramsey's theorem for pairs. Every coloring of pairs has an infinite monochromatic set. Hold that proof in your head and imagine that you have some family of sets H, and you would like to use that proof to show that there's a monochromatic set in your family H. What must be true about H in order for this to work? Well, the first thing you'll observe is that it doesn't make the problem any easier to assume that H is upward closed, so we will assume that. And the second thing you'll notice is that, forget about colorings of pairs. If you color singletons, you'd better have some sort of pigeonhole. So if some finite union of sets is an H, then one of the sets must have been an H to begin with. And the third and most interesting condition is that is this diagonalization condition. So in the proof of Ramsey's theorem, you do this thing where you find for each integer n a bunch of later n that are colored well with respect to the n that you chose, And then you go through and do a diagonalization where whenever you add an n, you commit later to add only later m's that are colored correctly with respect to n. So that's exactly what this this condition is saying. I suppose you can't see my cursor, eh? I have to use the annotation or whatever if I want to draw on the.
We can see it. I can see it.
You can see my cursor spinning around right now?
Yes.
Yeah, we can see.
Oh, I had no idea.
Yeah, we can
Okay,
see.
well, great. Then I won't bother with the annotations. Okay, so that's exactly what this third condition is saying. It is just the natural condition that comes out of the proof of Ramsey's theorem. Maybe I won't say too much more about it.
Okay, sorry, can I just ask about this third condition?
Yes.
Is it, I mean, because obviously a lot of times when you talk about, you know, filters like this, you talk about having sort of a pseudo intersection for descending sequences, and this is kind of a strong way that this happens.
Yes, it is stronger than that. Yes,
it's stronger than that. Okay, great.
So we're not just saying that there is, for every decreasing sequence, a set that is modulo finite, a subset of each term in the sequence. We're saying more. So yeah, I mean, this is not even equivalent, even for ultrafilters, this is not equivalent. This is the difference between selective and p-point ultrafilters.
Right, that's what I was wondering. Okay, thank you.
Yeah. So, okay, so the first two items here are really just this is just the definition of co-ideal. It's what it means to be the complement of an ideal. So it would maybe, in some contexts, it would be more natural to talk about the ideals, but because of this, the selectivity condition is more naturally thought of as a condition on the co-ideal, I think. So I'm defining it in terms of the complement of the ideal, but of course, they are both there and they will both come up. Okay, maybe I should mention that for a co-ideal it is not equivalent for a co-ideal to be selective and to be Ramsey, so-called, meaning solve all of these two-dimensional Ramsey problems. That's much weaker than to be selective. They are equivalent for ultrafilters. That's a theorem of Kunin, but they are not equivalent for general co-ideals. That will sort of come up later. What are some examples? This family of all infinite subsets of omega, it should be our favorite example of a happy family. Ramsey ultrafilters or selective ultrafilters would be the other natural example that will come up in this talk. I guess a third example will also come up in this talk. If you take an infinite mad family, I'll say a little bit more about this in a few slides. If you take an infinite mad family, look at the ideal that it generates, and the complement of that is a happy family. This is due to Matthias. So is the definition of happy family, and as far as I know, the name. Okay, so these are some objects that come out of Ramsey theory, and at least as I presented to you, the definition is motivated by finite exponent Ramsey theory, but of course it's natural to wonder what happens for infinite exponent Ramsey theory problems. If you partition all infinite subsets of omega into two nice pieces for L, something like that, and you have off to the side some happy family, must there be a monochromatic set for the partition in your happy family? What I just said, the answer is yes. If it's a Borel partition, this will come up again in a couple of slides. It is a theorem of Matthias that generalizes the Galvin-Prickry theorem. I think I keep clicking over to zoom and then the arrows don't work anymore. Okay. Here's a little beamer trickery. Here I have the definition of just what it means for a set of reals to have the Ramsey property. That just means that there is a set Z, which is monochromatic for the set as a coloring, meaning that either all or none of the subsets of Z belong to the set X. So I'm just going to strengthen that and insist that the monochromatic set come from our happy family H, some happy family H. Okay, I think there was supposed to be a pause between these two definitions. Some beamer trickery that didn't quite work out. H doesn't have to be a co-ideal for this definition to be interesting, but and I will mention a couple of contexts later in the talk where it does have to be it should be a co-ideal, but it doesn't have to be a happy family. And I'll mention some contexts later in the talk where it is not. Okay, so the Ramsey property relative to a happy family says that there is a there is a monochromatic set that is a member of the happy family. So we think of that as being positive because the happy family is a co-ideal, so it's positive relative to the ideal of which the happy family is a complement. Okay, and on the face of it, unrelated definition, a mad family is, this is a generalization of a partition of omega. So it's like a partition of omega, except we don't insist that the pieces be actually disjoint. We insist only that they be disjoint mod finite. So they have only, any two of them have only finitely many elements in common. And it is maximal with this property. According to me, there are finite mad families. According to my definition, there are finite mad families. You partition omega into finitely many pieces, you get a mad family. But of course, those aren't very interesting. It's the infinite ones that are more interesting. And they exist by an argument that makes use of the axiom of choice, a Zorn's lemma argument, if you like. Though this use of the axiom of choice is necessary by theorem of Matthias, we'll see in a few slides. And an easy diagonalization shows that no infinite countable almost disjoint family can be maximal. In other words, no infinite maximal almost disjoint family can be countable. So there's an associated cardinal characteristic that you maybe have seen something about, the least size of an infinite maximal almost disjoint family. Okay, but what do these things have to do with each other? The point is what I guess already said in a previous slide. If you take a mad family, it's made up of kind of like very sparse, very low sets, and you take the ideal that generates, then the complement of that ideal is a happy family. This is where the terminology comes from. And what's more, this happy family, generated in this way by a mad family, cannot be Ramsey relative to itself. Why? Well, there's a partition of infinite subsets of omega into two pieces, the ideal and its complement. And if you have a monochromatic set for this partition, well, it can't be in the co-ideal, because if it were, then you'd have a set, all of whose subsets are not coverable by finitely many members of the mad family, but this contradicts madness, you can show. The most substantive element of this, the point block, is that the co-ideal dual to a mad family is a happy family. That is some diagonalization argument that's due to Matthias. Okay, so Matthias has given us some tools for proving that infinite mad families don't exist. You just prove some infinite exponent Ramsey theorems, of which the following is an example. If you have an analytic set, if you partition infinite subsets of omega into an analytic and a co-analytic piece, then this partition is Ramsey relative to every happy family. It is maybe worth emphasizing already now, because it will be important later, that there is no definability restriction on the happy family itself. So for example, it could be some nasty thing. It could be an ultrafilter, or it could be some nasty thing generated by a mad family. Nasty in the sense of definability. Okay, and how do you prove this theorem? Not how do you prove this theorem, rather, how do you derive the corollary? I will get to the proof of the theorem in a moment. How do you derive this corollary that there are no analytic infinite mad families? Well, if you had an analytic infinite mad family, you would get a you get an analytic partition of infinite subsets of omega that is not H Ramsey for the happy family dual to this mad family. That would contradict the theorem. So there are no analytic infinite mad families. So this is maybe the prototype of a proof of non-existence of infinite mad families in some point class. Prove that the point class has nice infinite exponent Ramsey properties. Okay, Now this theorem, I hope, is going to reappear, excellent, on the next slide. So forget about the corollary for a second. We do care about mad families, but let's focus on this Ramsey property for a moment. Okay, so Matthias actually, even in his original paper, Happy Families, gives several proofs of this theorem. I want to focus on the one of them that we will generalize, of course. And there are now quite a few available proofs of this theorem. But the one I want to tell you about, which again is in Matthias's original paper, is it uses an absoluteness argument. Okay, so what do? We have some analytic set, partition of omega to the omega into an analytic and a co-analytic piece. And we have some happy family. Well, the first thing to do is take a countable transitive model M with the code for the analytic set. Sorry, I just have to move my windows over slightly. A code for the analytic set. It should also have the happy family and be sort of sufficiently correct. It should be a nice model that you got by taking an elementary submodel of a large rank initial segment of the universe, not just some random countable transitive model. Okay, this is maybe just a sketch of the argument. Okay, so you have this countable transitive model with everything that we care about. Over countable transitive models, we can find generic reals. And so the forcing that's relevant here is Matthias forcing guided by the happy family, which means just like regular forcing, except you insist, regular Matthias forcing, except you insist that the commitment be an element of the happy family. This has the usual properties of Matthias forcing, the Matthias property and the Prickry property. Matthias property, also known sometimes as hereditary genericity, and Prickry property, often called pure decision. Nope, I've done it again. There we go. Okay, so we can find a real generic over M for this forcing. That's fine. But it is important that we can find this real in H, the happy family, because the real is going to be our monochromatic set. Okay, remember that X is H Ramsey means that there is a set in H, all or none of whose subsets belong to X. And this really uses the third condition in the definition of happy family, the diagonalization condition. I mean, you can sort of imagine what's going on. You need a characterization of genericity that I haven't told you about for this Matthias forcing, but the idea is you get into the dense sets in M one at a time, and you need something kind of at the bottom, right? And you use the diagonal, the selectivity condition to get the thing at the bottom. Okay, so it can be found in H, great. And then the Matthias property of this forcing says that every subset of the generic is also generic, infinite subset, of course, is also generic. And the Prickry property gives us enough homogeneity to conclude that in the generic extension, all of these subsets of our generic real will be decided in the same way. It will be decided in the same way whether they belong to X. Okay, so that sounds good. But at this point in the argument, we have not used that X is sigma 1, 1. We just used in this third bullet point. Well, okay, we kind of have used, yeah, okay. What I said out loud did not use that X is sigma 1, 1, but the third bullet point does. So in the generic extension of M, there are many subsets of the generic real, and it is decided in the same way whether they belong to X or not. So that sounds like it's going to be monochromatic, but actually there are many generic extensions of M for different subsets. That sounds like it's going to be monochromatic, but these generic extensions of M may be wrong about what belongs to X and what doesn't, except that they're not, of course, because X is sigma 1, 1. So that's the important thing. We need the generic extensions, it should say, of M to be correct about membership in X, which is true, of course, if X has a sigma 1, 1 definition by Mostovsky absoluteness. Okay, so this is what we would like to, I think there's another thing. Yeah, this is what we would like to generalize to get Ramsey properties and then non-existence of infinite mad families for larger point classes than just sigma 1, 1. Okay, that seems maybe that was kind of fast for people. People haven't seen this before. Are there questions at this point?
Zach, I just had a question, kind of like a general question about happy families. It seems like maybe they're like on their way to being like a measure or a filter or like an ultrafilter with some like completeness properties or something.
Yeah, there is a strong analogy between Ramsey ultrafilters, which are the happy families that are ultrafilters, and normal measures on a measurable cardinal.
Oh, really? Wow. Okay.
Yeah, I mean, the definitions maybe kind of look the same. This like selectivity condition is kind of like a normality, and I guess there is a precise connection in that the selective ultrafilters and normal measures on measurable cardinal, maybe, and their isomorphic copies, I guess it must be, are exactly the Rudin-Kiesler minimal ultrafilters. Full stop.
Oh my gosh. Okay.
So yeah, there is a strong connection, but notice that these are co-ideals. We will care specifically about the case where they are Ramsey ultrafilters later, but like, for example, the ones that are dual to mad families are not ultrafilters. They're just complements of ideals.
Okay, I was gonna ask that too about mad families. Are they like on their way to, I mean, they have a little bit of finite intersections, but are they on their way also to being like ultrafilters or like measures?
No. So the ideals they generate are definitely not prime.
Yeah.
Which means the corresponding happy families are not ultrafilters.
Okay.
Yeah, I mean, there might be a suitable sense in which they're kind of small. Yeah, because like the ideal generated by a mad family is tall, so-called, meaning that every infinite set has outside the ideal has an infinite set in the ideal. So this is a kind of a measure of largeness of an ideal, but not really, I guess. There are quite small ideals that are nonetheless tall. So yeah, I think the happy families dual to mad families are even still quite far from being ultrafilters.
Oh, okay. Thank you very much.
Sure. Okay, but this fourth bullet point is the one to take away. The key ingredient we need to run this argument, if we are going to change sigma 1, 1 to something else, the key ingredient we need to run this argument is sigma 1, 1 absoluteness. We need these tiny little countable generic extensions to agree with the universe about the definition of our set. Okay, so yeah, I mean, you can see how some more general absoluteness might be useful here. Okay, I emphasize that we use the selectivity, not just Ramseyness of the co-ideal in bullet point 2. Okay, so I guess that's the end of the combinatorial introduction. And now I want to tell you exactly what generalization of sigma 1, 1 absoluteness the rest of the talk is about. Okay, so I guess the origins of this story are in the late 90s with this theorem of Niemann and Zapletal. So under suitable large cardinal assumptions, which I will explain a little bit more about in a few slides, under suitable large cardinal assumptions, if you force with a proper poset, not only can you not change the theory of L of R, but in fact, there is an elementary embedding from the L of R, the ground model, into the L of R, the extension. And it fixes every ordinal and every real. Now I say there is an elementary embedding, but the end of the sentence tells us what the elementary embedding must be. If it fixes every ordinal and every real, well, we know what it is because every set in L of R is definable from ordinals and reals. So if we fix the ordinals and reals, we have to send it to the set with the same definition. For example, the set of real numbers has a nice definition, and it needs to be sent to the set of real numbers in the extension, which is likely a bigger set. We've probably added some reals. Okay, maybe some people haven't seen proper forcing before or haven't seen it very much. If not, for the time being, I'd say just replace proper with CCC, and you still get an interesting theorem that says a lot about what's going on. What we really need for the Matthias style arguments of the previous couple of slides is sigma closed star CCC. So the proper posets are a class of posets that include the sigma closed ones, the CCC ones, and are closed under finite iterations, among other things. So sigma closed star CCC will be included here. And then proper posets don't collapse omega 1. Maybe that's among their most important features. Now, before this theorem was proved, perhaps in the 80s, I think this is due to some combination of wooden and steel, depending on which exact instance of the theorem you're citing. Similar theorems were already known to be true. So in the presence of similar large cardinals, if you force, any set forcing actually cannot change the theory of L of R. But you can't hope to, even with with real parameters, but you can't hope to improve this theorem to something like this with ordinal, those old theorems to something with ordinal parameters, because L of R correctly computes omega 1, and you can force to collapse omega 1. So you need some condition like proper in a theorem like this. And in fact, proper is not the optimal condition. There is another one that I will talk about in a later part of the talk. So yeah, that is what you maybe call like light, the older theorems of wood and steel are maybe what you would call like light face generic absoluteness for all set forcing, not just proper forcing. And so this is a more restrictive class of forcings, but better absoluteness. Yeah, okay. Oh, yeah. And so you can see kind of how this is going to be relevant if, I mean, what we want to do is improve sigma 1,1 absoluteness to some kind of absoluteness of L of R statements. And this sort of thing is what we want. But in the proof of Matthias's forcing, or Matthias's theorem from a few slides ago, what we needed was agreement between a small countable generic extension and the universe, not agreement between the universe and one of its generic extensions. So we're going to the version of this that we want to use is really a slight variant, which I'll call the triangular version. And here it is.
Sorry, but before you get there, can I just ask one more theorem about
Please,
the
yes.
last one, and one more question about the last theorem? Maybe I'm just missing something, but I mean, if you have an elementary embedding of any kind, doesn't it have to fix all? I mean, from L of R of V to L of R of V of G, doesn't it have to fix the reals by elementarity? I mean, could it not fix reals? Just because you fix omega and then, you know, just say that this element of Cantor space has 1 in the nth place is pretty absolute.
Yeah, that's right. But it could conceivably move ordinals though.
Yeah, no, of course. Right.
Yeah. So maybe and every real should be in parentheses or something. But yeah. Thanks. Yeah.
Okay. Yeah. No. It's just to make sure I wasn't missing. Thank you.
Yeah, but it could move ordinals conceivably, but it doesn't. Right. In fact, there's some. Okay. Itai and I had some discussion a few years ago about this for the triangular embedding theorem. That you can get versions of it for non-proper forcings that do move ordinals. In fact, I guess even the regular embedding theorem, if you don't use that the poset is proper and you just run the proof, then you get an embedding that moves ordinals.
The critical point is omega 1. I mean, the old omega 1, right?
Yeah, I guess that's right. Sorry. Uh-oh. I think I must have cut out for a minute. Everyone is frozen for a second. Did Corey ask a question?
Yeah, you were frozen, but it looks okay now again. So.
Okay.
I think you answered my question also before you froze. So.
All right, great. Okay, and This is the way I'm accustomed to stating this theorem, but I'm coming around to the idea that actually maybe we should state it in the following way. So you start with this original pi. Oh, I didn't state the theorem. Let me say what is this triangular version? So you have you take an elementary submodel of some large v theta, countable elementary submodel, and you collapse it. Okay, that gives you an anti-collapse elementary embedding. Then if you find some generic for a proper poset over this tiny countable model, you can re-embed the generic extension into the large rank initial segment of the universe. But of course, not the whole thing, just the L of R of the generic extension. The proper is a key word here. And well, that is the main keyword, proper. So I'm coming around to the idea that maybe this should be stated slightly differently. So the original pi is fully elementary. So another way to think about this is that the fully elementary original pi extends to a map on the generic extension that's elementary for formulas relativized to L of R. So this is maybe a better way of stating the theorem. So the triangle should be much more acute. Like the L of R of v theta is way up here, and there's just a tiny little move, downstairs move from the little countable model to its little generic extension. Okay, so this is the triangular embedding theorem. It says that if you, and really I want it to be thought of as a principle, as an assertion, and it is true under suitable large cardinal hypotheses, but I will say a little bit more later about under other hypotheses under which it is known to be true. Like for example, if there are no large cardinals in the universe. Okay, so here's the triangular embedding theorem. In a few slides, I will tell you how you derive some interesting combinatorial things from it, which was the whole point in the first place. Maybe I should wave my hands a little bit about the proof in case you're interested. The proof of this version of the triangular embedding theorem is more or less uses the same tools as the proof of the Niemann-Zaputal original embedding theorem. It's an iteration trees argument. You iterate to make the reals of the ground model and the reals of the extension the symmetric symmetric reals, the derived reals of some symmetric collapse of the iterand. So this is where the large cardinal assumption will be something about iterability of a small model with lots of wooden cardinals. And the tricky business is this simultaneously part in what I just said. You need to make the ground model reals and simultaneously the reals of the extension, the derived reals of some symmetric collapse of an iterand. And this is where the properness of the poset is used. And it's a complicated argument, but that you should at least know where properness comes into it. So it is a lot of work with Wooden's genericity iterations. But this version is more or less, I mean, it was not stated until my paper with Itai a couple of years ago, but it is more or less the same ideas as the proof from Niemann-Zaputal in the late 90s. What we need new ideas for, or more ideas, are to prove an analog under 80+, which I hope is the next slide. Yes, great. Okay, let me tell you a little bit about 80+. It is an extension of AD that is an attempt to axiomatize the models of AD, or at least attempt to axiomatize the models of AD that we know how to build. So it's conjectured to be equivalent to AD. I think that's fair to say. I think maybe Wooden conjectured it to be equivalent to AD. I don't want to put words in his mouth, but I think that's correct. Anyway, it's not known to be equivalent to AD is something that's definitely true. And I don't want to say all of the, I don't want to give you a precise definition of it here, because in some ways that's orthogonal to the purpose of the talk. But maybe the most important component of 80+ for the purposes of this talk is it includes the assertion that every set of reals is infinity Borel. If you have not seen infinity Borel sets before, the thing to think about is sets with the so-called Solovay property in the Solovay model. So it's like that, except you don't have a real parameter, you have some funnier thing, but don't worry about that. It's similar to the Solovay property. So every set of reals looks kind of like a set a set of reals in the Solovay model. Another ingredient in the definition of AD+ is dependent choice for reals. Unfortunately, AD+, the full dependent choice might not hold when AD+ does, and even in interesting situations. And this makes theorems about proper forcings in countable elementary submodels kind of annoying to state. Because in the absence of dependent choice, where are the elementary submodels? So what does properness mean? Properness is usually defined in terms of countable elementary submodels, but if there's no dependent choice, they may not be there. That's a scary world to live in. So I won't give you the precise statement, but I'll try to give you a vague sense of how you turn this into something that can be stated in a coherent way and used to prove theorems under AD+. So in the possible absence of dependent choice. Okay, so the class of posets are not proper posets according to the usual definition, but so-called absolutely proper posets. So we insist that their conditions can be coded by reals. So think of Mathias forcing or something. Conditions can be coded on by reals, definitely. And then we can look at all of the many inner models of choice that exist under determinacy. And we can ask for the poset to be, for its approximations to be proper in these ZFC models that are slowly approximating L of R. That's kind of what it means. Okay, that's quite vague, but I can say maybe a little bit more about that at the end, or you can go look at our paper for the precise definition if you like. Okay, so it's stated for absolutely proper posets, and then you get to a similar commuting system of embeddings, but not just with L of R's here. You also need some additional set. I mean, in addition to R, L of R and some additional set. Okay, how do you prove this thing? The main additional ingredient that you need, I mean, it's still at its heart an iteration trees argument. The main additional ingredient that's needed, which I didn't put on the slide, the main additional ingredient that's needed is the fact that under AD+, roughly, every true sigma 2-1 statement reflects to an iterable model with omega wooden cardinals. This is a fairly difficult result from inner model theory that I will not ask you to try to understand the proof of on a Friday afternoon looking at slides on the computer at the end of the semester, no less. But that is the main ingredient that's needed. That is absent from the usual triangular embedding theorem setting. Every true sigma 2-1 statement reflects to an iterable model with omega wooden cardinals. And the failure of the embedding theorem, or a suitable fragment of it, can be expressed as a sigma 2-1 statement. Then you reflect down to this iterable model, and you roughly imitate the argument from Niemann and Zapletal, though there are some additional things to worry about because we're working under AD+ and not in L of R under large cardinals. Okay, but we have a version of the triangular embedding theorem that holds under AD+ and is good enough to get the combinatorial applications that we want, which I hope are right here. Yes, excellent. Okay, so I have told you what the triangular embedding theorem says. I'll probably revisit this slide several times. It says that if you have a countable model that embeds into the rank initial segment of the universe, that embedding extends to a generic extension of the countable model by a proper poset to an embedding that is absolute for, or that is elementary for formulas relativized to L of R. So what do we use that for? First, every set in L of R is Ramsey relative to every happy family. Oh, and here are the large cardinal hypotheses that I suppressed earlier. So assuming the minimal model for omega wooden cardinals and its sharp exists and is suitably iterable, this should be size of the reals +1 iterable, probably, since I did not assume CH. So assuming these, something that is just epsilon more than the hypotheses you need for determinacy in L of R gives you that every set in L of R is Ramsey relative to every happy family H. This was proved by Todorcevich from stronger large cardinal assumptions. And so I should say corollary. Oh, how did I not put that on the slide? That's a mistake. Corollary, draw this in on your slides at home. Corollary, there are no infinite mad families in L of R under these hypotheses.
Zach, could I just ask you a quick question about this triangular version of the embedding theorem? I guess, so there's always, I guess, one embedding from L of R of M to L of R of M of G that fixes the ordinals and maps everything to what its definition would be evaluated in L of R of M of G, right? And so are you saying that, but it could be that there are other embeddings also.
I mean the inclusion on the bottom. Yeah.
Oh, okay, I see.
Or, or rather, not the inclusion, but the embedding that you described. Yeah, sorry. I should have.
Okay.
Yeah, I should have made that clear. Yeah, the embedding at the bottom is the natural one.
Okay.
I don't know what happens if you.
So you're not saying that there is always a pi hat that. I don't know. I guess that.
I'm saying that pi hat just extends pi for the purposes of. Yeah.
Well, it makes.
Well,
okay.
Yeah.
So you're talking about basically making this diagram commute when the embedding on the bottom is the natural one.
Yeah. This is probably stated slightly more carefully in our paper, but of course, when I copy it to slides, I omit some things. So yes, you're right. The bottom embedding is the natural one, the one that sends a set with a definition to the set with the same definition in the generic extension. That's right.
It's interesting.
Thanks for pointing that out.
Just from looking at the diagram, it looks like this realization property, like when you have a mouse and you embed a countable one into it, and then you take an outer power and you can realize it back into the original.
Yeah.
Mouse, right? So, and you could iterate this too, and so on and so forth. It kind of looks somehow similar to that.
I don't see a direct connection, but certainly the pictures look the same.
Yeah.
Yeah. I mean, one of the things I hope you all will get out of this talk is that I think there are applications of this this principle that are not known yet or haven't been observed yet.
All right. Thank you.
Yeah. Okay. So I was here. Yeah, so this was known from large cardinal assumptions before. Todorcevich showed this in the 90s, I think. Oh yeah, and the proof. What do? Well, you repeat the proof of Matthias's argument from many slides ago, and you look at the bullet point that says something about sigma 1,1 absoluteness, and you delete that and you replace a reference to the triangular embedding theorem. So what we needed to be true was that when we took our nice countable model, we looked at a little countable generic extension, that little countable generic extension was agreed with the universe about some formula. And that's exactly what the triangular embedding theorem gives. Okay, so.
Okay, I had a question.
Go ahead.
Okay, thank you. I know that you're trying to prove like some like monochромicity, like you're trying to, is that right? You're trying to prove like you have some kind of monochромicity, like and that's like really powerful. But okay, I think you said at some point the absence of DC is scary. Did you say that?
I probably did say that.
Yeah. Okay. Why is that? Or maybe you're asking too much or something, wanting too much.
Under 80 plus, DC really might fail. DC for reals holds, but a dependent choice, full dependent choice might fail. You can have, theta of countable cofinality, all kinds of crazy nonsense. But if DC fails, then you can't build elementary submodels or countable elementary submodels, right? And I think this is even more or less equivalent. So things like properness and embedding theorems with countable models, you really have to do some work to restate them in a context where there is no dependent choice. And what we did was basically just try to approximate the universe where dependent choice fails by nice inner models where it holds. And then, yeah, I mean, that was good enough for our purposes. Maybe there is a better, you know, in no way are we asserting that this is the optimal triangular embedding theorem under 80 plus. It is possible that there's something nicer. We also went kind of out of our way to prove a lemma that gives both the version 1 of the triangular embedding theorem and the 80 plus version. And you know, that may not be optimal either.
Okay, thank you.
Sure. Yeah, okay. So we get this Ramsey property relative to happy families and also the non-existence of infinite mad families in L of R from large cardinal assumptions that are just epsilon above the ones needed to get AD in L of R. Yeah, let's look at the second result and then compare them. So using the 80 plus version of the triangular embedding theorem, we get a similar thing. Under 80 plus, every set is H Ramsey for every happy family H. Consequently, there are no infinite mad families. So here I put the corollary, but not in the first theorem. Fine. Let's suppose that you are working under large cardinals. You have a supercompact in the universe or something, and you're looking at L of R where 80 plus holds. If you apply the second theorem, you get a weaker result than if you apply the first theorem, because the first theorem refers to happy families that might be outside of L of R, especially like Ramsey ultrafilters, for example. So that will come up a bit later, I guess. The first theorem is stronger when it is referring to when the second theorem is referring to L of R. So the second theorem you can think of as more of an internal. It's an internal fact. It is a theorem proved without choice, for one thing. Yeah, I mostly wanted to bring your attention to that because it will come up again later. Okay, so I think we're in the application section. So let's see some other applications. So assume the triangular embedding theorem holds. I mean, you can use this to prove that all of the usual regularity properties in addition to this Ramsey property relative to happy families business. How do you do this? Well, you use Solovey's original proof for the Solovey model in effect. What did I say about this? Almost nothing. I mean, Solovey's original proof, you collapse up to an inaccessible cardinal, and you do some. You reflect down to an initial segment of the collapse that has access to the parameters defining the set that you want to prove is measurable or something. And then you use the homogeneity of the collapse to relate this smaller collapse to the full collapse, the model with less collapsed to the model with everything collapsed. So you run a similar argument here, except you use the triangular embedding theorem instead of the homogeneity of the collapse. But the same basic thing works, that you want it's the Boolean value of the formula defining your set of the name for the generic real that witnesses that the set is measurable or has the Baire property. It's the same sort of thing.
Wait, sorry, but I mean the Solovey model, that collapse is very much not proper.
Yeah. But the difference is the Solovey model is the two sides of the isosceles triangle, not the bottom. So that you're reflecting information about the full Solovey model to models where you've collapsed only a little bit.
I see what you mean.
Yeah.
Right. So you just work with Okay. Yeah, that makes sense.
So it's like a countable submodel, right? A countable elementary submodel.
Right. Yeah. Okay. I see. Thank you. Sorry,
I mean, you could formulate Solovey's original argument that way, I guess. There's just no reason to, because you might as well take all of V and a little bit of the collapse. Okay, so this was, so this is nice. It doesn't give new proofs of Lebesgue measurability or Baire property in any context that I'm aware of, but it is worthwhile to observe anyway. Here's a more exciting application. So this is William Chan and Magidor were working on these canonization results. There's this whole program of understanding when for example, an equivalence relation with nice classes is on a large set nice. If the classes are nice, can we restrict to a large set on which the equivalence relation is nice? And the triangular embedding theorem gives an alternative proof, well, a proof that gives a little bit more actually of one of their theorems. Okay, so let's assume that the triangular embedding theorem holds. We have a sigma ideal on the reals for which the associated Zapletal forcing is proper. Okay, the forcing is force with Borel I positive sets. If you have not seen this before, pretend that I is the sigma ideal of null sets, and this is just random forcing. So you're forcing with Borel sets of positive measure, trying to add a random real. And this is going to say something about canonization on a measure one set under those circumstances. In fact, I wish I had done a Beamer trick to make it look like that, but too late. Next time. Okay, now we have an equivalence relation that belongs to L of R. And my R's are, this is the reals, of course, and R is an equivalence relation, light face R. It belongs to L of R, so it's pretty nice. And let's say it has gamma classes, where gamma is some nice point class with properties to be specified in a moment. Then there's one, and in fact there are densely many, I positive Borel sets B, restricted I restricted to B, restricted to which R is in gamma. That should be R, not I. What a terrible typo. R restricted to B is in gamma. Okay, I like to eliminate unnecessary parameters when they distract from the substance of the theorem. So if you just pretend gamma is sigma 1, 1. I did not pretend that in the following proof, but it's easier to think about, I think. So if you have an equivalence relation that belongs to L of R, you can also pretend that it's the Borel sets. With all Borel classes, then you can restrict, and you have some sigma ideal like the sigma ideal of null sets. You can restrict to the equivalence relation to a positive set on which the relation itself is sigma 1, 1. Now, can I just, what if I do that? There, perfect. Oops. Can you no longer see my screen? I've somehow done something disastrous. There we go.
It looks good. You can see that.
Oh, okay, okay. It said your screen sharing is paused, but I think it was lying.
Well, it's good.
So
All right, thanks.
what does it mean that P sub I is proper? What is that?
Okay, so P sub I is the forcing where conditions are positive, I positive Borel sets. So it's just like random forcing where I is the null ideal, or like Cohen forcing when I is the meager ideal.
Okay.
So this is something that has been studied extensively by Zapletal in this level of generality. And there are other interesting cases where it is proper even for like non-CCC ideals, right? Okay, so pretend that it is the null ideal if you want. That you still get an interesting theorem. And then I'm actually going to use gamma instead of sigma 1, 1, but replace every instance of gamma by sigma 1, 1 in your slides if you want. Oh no, now this is still here. So I have to erase that, I guess. I thought it was writing like on the PDF, but no. Okay, so here's the theorem. We are trying to find a positive set on which our relation is nice. Okay, so take an M as in the beginning of the triangular embedding theorem, a nice countable M came from collapsing an elementary submodel of a very large V theta. Okay, it's a nice countable model, so we can find over it a PI generic real, random real, let's say. You can find a random real over M. All E classes are in gamma, so in particular, the E class of this generic, this random real is in gamma. Well, gamma, it said in the theorem, but I didn't tell you, gamma has a universal set. So it's the analytic sets or something. It has a universal set. So we can find a name for which section this E class comes from. So there's a name tau. This is a fullness of the forcing language or whatever it's called. There's a name tau so that the E class of this generic real is forced to equal the tauth section of some universal gamma set. So in other words, if you want to think about gamma equals sigma 1, 1, we are identifying the tree of which the E class is the projection. Okay. So far, it seems like we've done very little. Okay, and then the point is that this generic extension is correct about E because E came from L of R and we assumed the triangular embedding theorem. So this is something that I guess there were probably, I don't know the history here, but there were probably canonization results that just used Mistovsky absoluteness for analytic equivalence relations well before this CHAN-MAGIDOR business, though. Like I said, I'm not totally sure about the history of this work. Okay, so M of G certainly thinks, by the forcing theorem, it certainly thinks that the class of the generic real is this particular section of the universal set. And it is right, because it is correct about E, because E came from L of R, and we assumed the triangular embedding theorem. Okay, of course, the positive set is going to come from a set of reals that are generic over M. So look at the random reals, let's say, the reals that are random over M. This is a non-null set by a standard argument. And in general, you need that, this is the point at which you use that PI is proper. Okay, so now we can actually see how for random reals over this little model, the equivalence relation canonizes to something that is nice. It's in gamma. Okay, so how do we tell whether two things are related? Well, if we have two generic reals, then one is related if and only if they're related if and only if one is in the particular section of the universal set for the other, because that's the same as its E class. But this condition, saying whether X2 is in this particular section of the universal set, is in gamma by closure under Borel substitutions, which is the other assumption about gamma that I didn't tell you. And this uses that M is countable, of course. We need a countable model so that this is a Borel substitution. So using the fact that generic extensions can be made to agree with the universe about L of R formulas, we can reduce the question of determining equivalence in this equivalence relation to something much nicer. Just asking at the cost of reducing the field of the equivalence relation, of course. But we can make it I positive. We can make it, positive measure or non-meager or number of other reasonable things. So this, I hope you'll take as evidence as that there are likely to be other applications of this theorem that have not yet been discovered. Cool applications. Okay, I think maybe let me just make a couple of remarks about this proof while you're still digesting it. The first thing to say is that just like with random forcing, the generic for the forcing uniquely determines a real, like the intersection of all of the elements of the generic filter is a one element set of reals. Just like for random forcing, I think I just said that. Conversely, if you have a generic real, that uniquely determines the generic filter that it came from, and that's used, I guess, in this bottom part of the argument where I give this undefined notion Gx1, which is the generic determined by the generic real x1, generic filter determined by the generic real x1. That's what I thought. So this is the end of the application section. So maybe, I think this would be a good time to stop and see if there are questions. Not stop for good, but stop temporarily.
Is there a way to phrase this theorem to tell me something about like how the, you know, how the generic reals for PI interact with this particular equivalence relation I might be interested in? I mean, you know, is it saying something like, you know, all Cohen reals are going to have such and such property or something like this?
You might be able to get something like that out of the proof. I mean, okay, so the proof says that you can find lots of reals that are generic over a countable transitive model, so they're pretty, you know, pretty generic, on which the equivalence relation is nice. Yeah, I don't know.
Okay, thank you.
Yeah, maybe I didn't fully understand your question, but I think probably you could get a more interesting, let me say this kind of orthogonal. Probably you could get something more interesting by looking at particular I's here, like especially null and meager, and then maybe some of the other ones that, the particular examples that Zapletal has considered.
Right, yeah,
So,
I think that's what I was sort of thinking, but I think I'm still digesting this, so sorry, yeah, no, that makes sense though.
I will say that the gamma can be quite a lot here. I said it could be sigma 1,1. It could also be delta 1,1, the Borel sets. I think maybe that was known before Chan and Magador. The result was known before Chan and Magador, but actually maybe not. No, I take that back. I think the things that were known before Chan and Magador is if L of R is changed to some rather stronger assumption, changed to a stronger assumption. Oh, that's what we just did. Okay, consistency strength. So natural question, if you see these things, okay, we got the embedding theorem, both the triangular version and the original version by wooden cardinals plus epsilon, basically. What is the exact consistency strength of these theorems? I think it was thought at the time that the consistency strength would be roughly consistency strength of AD and L of R. That you should be able to recover the wooden cardinals that were used to get the theorems in the first place. But that turned out not to be true. So yes, paradise can be approximated by forcing over L, as we know too well. You know, if you just want some consequences in determinacy, you can often get them just by forcing over L, like a Solovay type model. If you just want all sets are Lebesgue measurable, have the Baire property, and so on, you can force over L to achieve that. If you just want every set in L of R is Ramsey relative to every happy family, you can collapse a Malo cardinal to get that. If you just want, you know, what other example do I have in mind? If you just want the triangular embedding theorem, you just need to collapse a remarkable cardinal, which can exist in L. Remarkability I won't define here. I can tell you at the end what it is if you're interested. But yeah, Schindler showed that if you collapse a remarkable cardinal, then you get the embedding theorem for proper posets. For proper posets is a key trio of words. And conversely, this remarkability is optimal. If you haven't seen remarkable cardinals before, here are two important facts. The first is that they can exist in L, so their existence does not imply existence of zero sharp. And the second is that it's stronger than weakly compact. So it's somewhere in between weakly compact and zero sharp, but strictly below zero sharp. That's important. And then a little advertisement for a different theorem with Itai. In the theorem, in Schindler's original result really used properness. It's not, it does for the lower bound, the second part. He really used properness. And so we improved proper to sigma closed star CCC by giving a more or less totally different coding argument, which I think is what I discussed the last time I spoke in the CUNY set theory seminar a year or two ago. So you all already know about that. Okay, what about the triangular version? This is the Niemann-Zapletal embedding theorem from the universe to its generic extensions. What about this internal triangular version? Well, someone, I think William Chan or maybe Schindler, observed, probably both, observed that you also get the triangular embedding theorem in this model. If you collapse a remarkable cardinal to be L(1) by cannibalizing everything below it, then you get the triangular version of the embedding theorem, again, for proper posets. Okay, but this is achieved by forcing over L, so this doesn't imply any non-trivial amount of determinacy, which I think was unexpected at this time in 2001. I think the expectation was that you could at least get pi11 determinacy from this embedding theorem, but you can't. Okay, good. Okay, let's take a sharp turn back to combinatorics for a moment. Let me remind you what selective or Ramsey ultrafilters are, which have maybe different definitions, but are equivalent. An ultrafilter on omega is selective if every function from omega to omega becomes constant or one-to-one when restricted to a suitable set in the ultrafilter. These are exactly the happy families that are ultrafilters. That is an equivalence. It is the theorem of Kunin that U is selective if and only if it solves all of these two-dimensional coloring problems. Remember from the beginning, though, that that's not true for co-ideals. It is true for ultrafilters. Okay, so in particular, all of these theorems I quoted earlier about happy families also apply to selective ultrafilters, or Ramsey ultrafilters, if you like. Okay, first thing, a couple of observations. First, notice that if you force with power set omega modulo the finite ideal, the generic ultrafilter must be selective. This is much easier to see by using Kunin's characterization than the definition, because it's just Ramsey's theorem. There are densely many monochromatic sets for any particular coloring. Something in the other direction. I almost said converse, but definitely not, or not really. Something in the other direction. If you have this Ramsey property for all selective ultrafilters, which remember is a special case of happy family. If you have this Ramsey property for all selective ultrafilters, then the selective well, actually just, it's true ultrafilter by ultrafilter. Then the ultrafilter must be generic over L of R. Why is that? Well, look at a dense open set in L of R in P omega mod finite. It defines a partition of the infinite subsets of omega into two pieces. And this partition, since it belongs to L of R, should have a monochromatic set in U. But U can't very well, I mean, the color of the set can't very well be the complement of the dense set. So the color has to be the dense set. So U has to have an element in the dense set. So it's generic. Okay, so this is something that has come to be known as complete combinatorics for selective ultrafilters, because somehow if you're generic over L of R, then that should determine kind of everything about you. I mean, not literally, of course, but any sort of combinatorial fact about an ultrafilter should be totally determined if it is generic over L of R. I don't think I put this on the next slide. So Todorcevich showed that under large cardinals like supercompact, I think, that this complete combinatorics for all selective ultrafilters holds. So that follows from the earlier theorem of Todorcevich that I mentioned in passing. And so Itai and I get a version of that with lower large cardinal strength. But if you just ask for consistency, the consistency is much lower. So Matthias showed this in the original Happy Families paper. If you Levy collapse a Malo cardinal in the resulting model, you get complete combinatorics for selective ultrafilters. And then in the 90s, Todd Eisworth showed that this malo is necessary. For Eisworth's half of the argument, if you're interested, he shows that if ALF1 is not malo in L, somehow too much information can be coded into a selective ultrafilter under that assumption. Like, for example, a well ordering of the reals, something like that. Oh yeah, but you need some assumption.
That's awesome. That just sounds really cool.
Yeah, I like that proof a lot. But somehow you need some assumption to actually build the selective ultrafilter in the first place, because they may not exist. So CH is suitable. I would be happy to be proved. I would be happy to be told that I'm wrong, but I think it is open what the consistency strength of MA-ALF1 plus complete combinatorics for selective ultrafilters is. I think that is open, and I conjecture that it is more than the malo, but it could be that that's known. I'm not sure. Yeah, I think that's open. Okay, a quick, no, not a quick detour yet. Yeah. Okay, so this is why we know that the axiom of choice is necessary to build infinite mad families, because in this malo, in this model, you get not just complete combinatorics, but this thing that every set in L of R is Ramsey relative to every happy family, which gives no infinite mad families. So this is how is a little misleading. I mean, in this model, Matthias showed that there are no infinite mad families, which is now known to be consistent relative to ZFC alone. The malo, for that, the malo is not necessary. So hold that into your off to the side for a moment, because we'll return to it in the open questions section. Okay, I just want to say a little bit about reasonable posets. In hindsight, when I was preparing it, it occurred to me too late that this is a weird place to put this in the talk, but I apologize. The slides have to be linearly ordered, unfortunately. Well, I think they do anyway. So, okay, so remember that the embedding theorems all apply to proper posets, but if you go look at the proof, you don't need properness. You need something that's unfortunately known as reasonability. What's the definition? Well, you take the definition of proper and you switch some quantifiers around. So a proper poset is one for which there's a club of countable models for which every condition in the model extends to a master condition for that model. Reasonability says every condition for stationarily many models extends to a master condition. Why is this a good idea? Well, if you go look at the proof that proper posets don't collapse ALF1, you don't really need full properness for that proof. You need reasonability. So reasonable posets do not collapse ALF1. Let's see, what else do we need to know about them? Yes, and then the most important thing for our purposes is that distributive posets are, distributive posets are reasonable, whereas they need not be proper. So for example, the standard example is to shoot a club through a stationary, co-stationary subset of omega-1 by initial segments, closed initial segments. Okay, so everything I've said before up to this point is about the embedding theorems for proper posets, where the consistency strength is known to be exactly a remarkable cardinal. But for this broader class of reasonable posets, the consistency strength is open and it's much higher. Okay, I said that. Yeah, so even for just distributive star CCC posets, it is known to imply the existence of, the embedding theorem is known to imply the existence of sharps and much more. This is, I think, primarily due to Schindler. It's their core model arguments. So I think that the best result is something like an intermodel with a strong cardinal, something like that. But in any case, the consistency strength is much higher, and it is the exact consistency strength is not known. Okay, so this is relevant for the combinatorics for the following reason. Ilias Farah introduced these this generalization of happy families called semi-selective co-ideals, which are, you can think of as exactly the weakest condition on a co-ideal for all of the nice properties of the associated Mathias forcing to be proved. So you can still prove the Mathias property and the Prickry property and so on. And so, right. And so the triangular embedding theorem, version 1 of the triangular embedding theorem, since it applies to reasonable post sets, it also gives us a Ramsey property relative to these semi-selective co-ideals. The consistency strength of this Ramsey property is open, both upper and lower bounds. I mean, well, obviously, the consistency strength is open. Okay. And finally, some questions. I've already mentioned some, the most notable of which is what are additional applications of the triangular embedding theorem? I hope I put that on the slide, not this one. What are additional applications of the triangular embedding theorem, and some consistency strength questions that I mentioned before. Let me give a brief introduction for one more open question that I really like. So the exact large cardinal hypothesis needed to prove the triangular embedding theorem is the existence of the minimal iterable model for the sharp of omega wooden cardinals, M omega sharp, and some uncountable amount of iterability for it. So if you just want something nice and combinatorial about the reals, like this Ramsey property, size of the reals plus 1 iterability will be enough. But if the embedding goes up higher, then you need, if the post set comes from farther up in the universe, then you need more iterability to capture it. Okay, Steele's proof that PFA implies AD and L of R, in fact, gives this iterability assumptions. This is like hypotheses needed for AD and L of R plus epsilon. It in fact gives that. So even from failure of squares, which are known to follow from PFA. Okay, so PFA implies the triangular embedding theorem and its consequences, like complete combinatorics for selective ultrafilters. So like compactness assertions like PFA that aren't themselves large cardinal assertions. It could be that PFA holds and there are no large cardinals in the universe, right? Imply the triangular embedding theorem, and so we get its applications. Yeah, that's right. But what about just AD and L of R? Does it imply the triangular embedding theorem? And now I should clarify what this says, because you might be looking at this and saying, this is nonsense, you just proved a theorem that answers the question. But no, the original version of the triangular embedding theorem, the one about L of R, not about, not the 80 plus version. So it is true that the 80 plus version holds in L of R when 80 plus holds in L of R, but that is an internal version of the theorem. It just refers to post sets that belong to L of R, not the ones that live outside. So let me maybe state it out loud in a more precise form. Assume you're looking at V, assume that AD holds in L of R, and you have some proper post set in V. Must the triangular embedding theorem hold for that proper post set or a reasonable post set? It's maybe worth noting that you can't get that for free, or not for free, but you can't get it just from the proofs that I've described. AD and L of R does not imply this iterability hypothesis. So, maybe this is kind of an unreasonable question, because whatever the answer is, it's going to be pretty hard to prove, most likely. So maybe a better question is this one. Does AD and L of R imply complete combinatorics for selective ultrafilters? This is a nice concrete combinatorial question. And I really like it because if true, it would be exciting, because complete combinatorics for selective ultrafilters is like an external to L of R regularity property for sets of reals. So, of course, we know that AD and L of R, asserting AD and L of R says something about the universe, but this would be a nice concrete example of that at the level of combinatorics of sets of reals. Yeah, so this is actually the version of the question I like more. Assume that AD holds in L of R. Must every set in L of R of reals be Ramsey relative to every selective ultrafilter, and the selective ultrafilter comes from V. So it follows from my theorem with Itai that if you replace a selective ultrafilter by a happy family here, and you require that it belong to L of R, then the answer is yes. But the important thing is that the selective ultrafilter won't belong to L of R. So it's like an external regularity property. Yeah, so okay, it would be really cool. Probably, I don't know how to prove it without, I don't know how to prove it at all, of course, but I suspect that to prove it, you need some fairly big machinery of wooden to use some fairly intense consequences of AD and L of R in order to get something like this. Yeah, so it's a regularity property of sets of reals that is external to L of R. Okay, and that is basically where I want to leave you. And here, if you got nothing out of the talk, here's a nice picture of my dog. Nothing else out of the talk. Hopefully you'll enjoy that.
Thanks for that. That did improve me. Thank you. Thank you very much.
Sure. Okay, I almost made it to 90 minutes. Wow, I'm surprised, but it really shouldn't be. I said that I wouldn't take too long, so of course I spoke for forever. I'm not sure whether to leave up the picture of the dog or these two questions. But maybe if people have questions, I will decide based on that.
So are there more questions? Let's see, maybe I'll stop highlighting you if I can. I can't. Yes.
So I have a kind of comment.
Oh, great.
So we as Sander Müller and me studied a quite similar property. It's actually we called it internal absoluteness as well, and we studied this only for projective sets, and it's actually just equivalent to the triangular embedding theorem, but restricted only to projective formulas, so weaker form. And
no kidding.
So, well, yeah, and I just want to, because you're looking for applications, I want to add. So we also thought this is an extremely natural notion of absoluteness, and so, for example, if you we looked at forcings of the form pi, so Borel sets modulo a sigma deal where this is proper. So, so the triangular embedding theorem for forcings proper forcings pi restricted to projective sets formulas is also always equivalent to uniformization. So there's a descriptive reformulation of this as a kind of strengthening of regularity property. So uniformization is just a strengthening of the usual regularity property for an ideal. So
cool.
Kind of adds to the fact that this is very natural notion of absoluteness that you were stressing it.
Yeah. So probably the answer to one of my questions is no. Then, if it is equivalent to, well, maybe. Okay, but yeah, I would like to know more about this. Do you have a paper or something?
Well, it's not in the form to be sent, but I sent you slides, and I think it would be very interesting to study this in connection with H-Ramsey, the H-Ramsey properties you studied. So I'm not at all familiar with that.
Yeah, no, that sounds great. Good. It's a meta-mathematical sign that it is interesting if more than one person has more than one group of people has independently considered it.
Yeah, I just had a little comment about it, and I don't know how Philip and you guys formulated this, but you know, instead of thinking about it as an embedding theorem, I guess you could think about it as like, if you don't collapse this countable elementary substructure that you consider, and instead just leave it uncollapsed, it's an elementary submodel of your L of R, right? And then you look at, or of your V theta or whatever you formulated, then you have an M generic G, then you just get that M of G is still elementary in this, or the L of R of this M of G is still elementary in your original model, right? So it's very natural to think about it, because then it eliminates this saying there is an embedding that completes this or makes this diagram commute. It just means that that model that you get is elementary in the thing, right? And then it makes
Yeah.
sense also to look at, that was actually kind of a question I had, and Philip kind of answered it already. It would be natural to look at partial elementarity, you know, how elementary is it in the beginning and in the end, right? So Philip looked at, if I understood this correctly, projective elementarity, right? Yeah, but you could do, you could look at all kinds of variations, right? And another question I had was like, okay, so you played around with, I mean, of course you can play around with the complexity of the forcings that are allowed, but you could also, you know, I guess instead of decreasing the level of elementarity, go up. Like, for example, is there any way that you could get something for more complicated than L of R, like L of P of R or something like that? Just, you know, throwing things out there.
Interesting. I mean, I guess we get a little bit more under 80 plus, but that's also, I mean, not really a lot more.
Or who knows, K of R, or I don't know, like.
Yeah.
Yeah. Okay. All right. Any other further questions? I guess not. I mean, we had a lot of questions during the talk already, which is not surprising. It's a tradition. So,
Good. I like that.
Okay. So yeah, thanks a lot. Very nice talk. Interesting things to think about.
Yeah, thank you all for having me and for listening. I hope you go away and find tons of applications of this triangular embedding theorem.